Thank you very much for coming out for the Hyde lecture again tonight. I'm very pleased to have David Benjamin here today. David is founding principal at the architecture firm The Living, as you can see on the screen, and an assistant professor of architecture at Columbia University. He is part of I think part of a new generation of architects and designers who combine computation-driven design research with an interest in material intelligence. And I think the work is really quite fascinating in terms of the connection of that level of basic research with the design process and future potential in our industries and our fields. David's won many design prizes, including the Emerging Voices Award from the Architectural League of New York, the New Practice Award from the AIA, the Young Architects Program Award from the Museum of Modern Art PS1, fellowship from the New York Foundation of the Arts, the Architects, on and on and on and on, blah, 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 more awards. I'm not going to list them all. He's also part of the One Lab, which is a nonprofit research and education group that refers to itself as an interdisciplinary think tank and a pedagogical silo breaker zone, which I think is a very interesting way to define an organization. If you look at that organization's website, you'll see that the people involved are extremely diverse, I guess. It's one of the more diverse organizations you'll find. His firm, The Living, is a first-of-its-kind Autodesk studio, meaning that Autodesk purchased his company a number of years ago, and so he's connected with Autodesk very directly. And they explore the future of building by working on full-scale functioning prototypes as a basis for the research. And the projects apply generative design, biology, and new materials to real-world built projects in the context of technology, culture, and the environment. In 2015, The Living was ranked third by Fast Company in their list of the world's 10 most innovative architecture firms. And David's work has been exhibited at the Venice Biennale, the Victoria and Albert Museum in London, eSpace Foundation in Paris, Acadia in Calgary at the conference there, the New Museum in New York, the Nevada Museum of Art, New York Academy of Sciences, and at the TED Conference. It's also part of the permanent collection of the Museum of Modern Art. And before receiving his Master of Architecture degree from Columbia, David graduated from Harvard with a BA in Social Studies. And I know that sounds like sixth grade, but Social Studies is actually one of the more demanding concentrations at Harvard. It requires a thesis, it's multidisciplinary, and it's a lot harder than it sounds. So please join me in welcoming David Benjamin, and welcome to Nebraska. He may or may not have been here before, but thanks, David.
Great. Thanks, Jeff. Well, thanks a lot. It's a pleasure to be here, and thanks, Jeff, for the generous introduction, and thanks to Jeff and everyone for inviting me here. What I wanted to do today was describe a little bit about our thinking and our kind of approach to architecture. And in other words, what I want to describe here is an approach that thinks of design and of architecture as really an ecosystem with interconnected loops of ideas, culture, technologies, materials, humans, non-humans, and the natural environment in a way that each loop kind of doesn't make sense alone, but only kind of gathers its strength and its meaning and its relevance through its connection to other loops, through its kind of network effect. And in that kind of context, I would like to share a little bit about our thinking and our approach by describing several different projects, which could be understood as different loops in our design ecosystem, and several different approaches that we've been exploring over the past few years that we think are relevant to future possibilities for architecture and cities and the built environment. So many of our approaches involve bringing architecture to life in different ways, sometimes literally, kind of as you see in a prototype here. As Jeff described, many of our approaches involve this intersection that we think is very interesting right now of biology, computation, and design. But I think it's important for me to note, before I start getting into some of these examples, that our approaches are also about things beyond the technical. They're not just explorations of technology. They're not only driven by a material, but they're about the complex interactions that are always present in architecture between technologies and materials, and also things like public space and culture and aesthetics and atmosphere. So in that sense, I'm going to jump right in, and I'm going to try to quickly describe this series of approaches and projects and emphasize more than a single kind of completed version of a vision. I'm going to emphasize the interconnections between these different approaches and projects. I'm going to number these, and number 0, because it's the foundation for everything we do, is prototyping. And a few years ago, we invented a kind of research method that we call flash research based on prototyping. And we define flash research as an investigation that involves self-imposed limits. In other words, we have a limited amount of time, 3 months or less, a limited amount of money, $1,000 or less. But nevertheless, we try to explore a new architectural idea through creating full-scale functioning prototypes of that idea. And this gives you a sense of the way we make these prototypes. So they're iterative. We often try to make a functioning prototype every week. We improve upon the functionality. We add one feature at a time. Some of the experiments are kind of failed experiments, but this is how we kind of learn about an idea. And to give you a more tangible sense, one of our flash research projects started with a material called a shape memory alloy, or sometimes called a muscle wire. And this is basically a thin wire that contracts along its length when you apply electricity to it. This is a diagram of that material. The way it contracts is through a kind of molecular restructuring shown in this diagram. And in this flash research project that we call Living Glass, we, at the end of our research project, the end of 3 months, the end of $1,000 in prototyping materials, we created this, which is basically a thin, transparent surface that responds, that moves, that breathes in response to different triggers. So one way of looking at it is that it has sensors embedded in it, and it can be a substitute for glass that opens up when sensors are triggered. In other words, it's glass that's responsive, that's living. And after projects like this, we document them not only through photographs and videos, but through things like instruction manuals and source code and circuit diagrams. And that's because we see our projects, this kind of research, as part of bigger ecosystems, and because we want to be able to communicate what we learned from the project to other people so that they can kind of build off of it and take it in a different direction. And one example of that is a student project from a class we have been teaching at Columbia, where our students took the same material and the lessons that we taught in the first week, but took it in a totally different direction. So they've used this shape memory alloy to create what they call the Huggy Wall. And so we ourselves build off of our own flash research projects, and this is a project where we started looking at buildings and how buildings are increasingly having more sensors in them. But typically, buildings are keeping that sensor data to themselves, and we were imagining, what if buildings could share their sensor data with other buildings and create a kind of social network, or almost like a Facebook for buildings. And to explore that more specifically, we built some custom air quality sensors, some kind of simple custom software to track the data from those air quality sensors, and a larger version of this living glass, this breathing building envelope. And here you see a sensor, so this is detecting carbon monoxide and nitrogen dioxide, two important kind of contaminants in city air. We're connecting a simple radio to that sensor and a simple battery, and then we get these small boxes which we can install on the inside or the outside of a building. They can collect data and wirelessly send that to a kind of central control computer. Our first installation was on the facade of the Empire State Building in New York City. And the Empire State Building was sending its sensor data back to a gallery in downtown Manhattan where we had this big installation of the breathing building envelope. We did a second version where we had two different buildings outfitted with these sensors, one in New York and one in San Francisco, and they were sending information to each other in real time. So it was basically imagining that in the future, buildings could be collecting data about their world. They already are collecting data about their world, and they could share this with one another, and they could start to have a conversation. And in the end, they could start to do things like more efficiently schedule their consumption of energy to reduce total consumption of energy and peak demand and reduce carbon emissions. So that's some of the experimenting that we did kind of early in the process of our studio, and you can see how some of the outlets for this research were kind of self-initiated, and some were kind of gallery installations. And this is a project that was continuing that trajectory, but it was for the city of Seoul, South Korea. And this is kind of number one of our several points that we'll describe tonight, and it's basically about information. So this is one of the elements of our kind of design ecosystem, information. And the idea of this project was to start with air quality. These are two pictures taken on different days from the same vantage point in Seoul. You can see that Seoul, like a lot of other cities, has great fluctuation in its air quality. And Seoul also has this kind of unique kind of way of displaying air quality in real time. So in other words, on the left you see a billboard that's displaying a real-time number of PM10. That's an important particulate in air quality, or in the air. And on the right you see a website with a map of the city and different colors representing different air quality readings. Seoul, like several other cities, especially with a lot of new construction, also has this building culture of dynamic LED facades, and you see a lot of kind of rainbow patterns, and you see things like digital flowers moving around on a building. But our thought was maybe we could combine these two things, this network of real-time environmental quality information with dynamic building facades to get a building that's displaying something more than just a kind of pretty pattern. And the way we explored that was to start with a map of the city. These are the 27 different GUs, or neighborhoods, in Seoul. We located and developed a partnership with the municipal government to use air quality sensors that the government already has. These are located in the dots. We redrew the map according to air boundaries as opposed to political boundaries or geographic boundaries. And then we bent this map into a kind of a canopy that we could use as a physical version of a potential building facade and a prototype of a building facade of the future. And this allowed us to create a permanent installation in a public park in Seoul that was responsive and related to this ecosystem of information in a couple of ways. First, it was a display of air quality improvement. And the way it did this, and still does this because it's still installed there, is that it's a map of the city, as I described. Every panel corresponds to a neighborhood, and panels illuminate if their air quality right now is better than a year ago. So by looking at which neighborhoods are illuminated, you can see a kind of register of air quality improvement. Is the air quality getting a little bit better or not? In a very low resolution register of information. Second, it's a display of real-time air quality, and it does this because every hour the whole map goes dark and the panels illuminate in order of best current air quality to worst. So in this case, you're able to compare one neighborhood to another right now. In the previous case, you're comparing one neighborhood to itself over time. And finally, and this kind of gets at the ecosystem of communication and information that I was talking about, it's a display of public interest in the environment. And the way that works is we created a custom text messaging hotline. You can enter a zip code or a postal code, request air quality information about it, and then you see that the panel blinks twice, the panel corresponding to that neighborhood. Then you get back on your phone the real-time air quality of that neighborhood. But what we think is most interesting is that in addition to you getting some personal information in the way you're accustomed to navigating the world with your phone and your other devices in this ecosystem of personal information, in addition to that, you're adding your personal request, your personal thinking in a way to a collective, because the facade itself or the pavilion is a collective register of all of us requesting information. In other words, if you look at this pavilion and you see a lot of blinking, then you know a lot of people, the general public, are requesting information at that time. If you see one neighborhood blinking more than others, you know that more of us are interested in that neighborhood. And it's a kind of provocation to start asking questions about this data and to take this ecosystem of data that we already are very much a part of and put it in the context of a collective, not just an individual. So this is a construction in a public park. In some ways, it's like other works of public art, like public sculptures, but it really has this kind of secret mission to be an experiment about the building facades of the future and what the city might do if it came to life in this way, combining this kind of information with this kind of public interest. Number two, environment. So a project we did at about the same time drew on some of the same ideas, some of the same hypotheses that we were having, but it explored water quality in New York City instead of air quality in Seoul. And the way this worked was we created a floating network of lights in the East River. These lights were actually tubes, transparent tubes, about 6 feet long, half underwater. Underwater was outfitted with sensors, and half above water, and above water was outfitted with dynamic LED lights. And we used this kind of stuff, electronics, digital sensors. You know, we could loosely say that this is the building material of the Internet of Things. But recently, we've been adding to that biological sensors. So in other words, combining biosensors with digital sensors. And what I mean by that is that we're using living mussels. So these are mussels, the shellfish, same species that we sometimes eat. You see in a tank here that they're kind of jittering around, and that's because mussels, as part of their natural metabolism, open and close their shells. And it turns out that they open and close their shells at a rate and an amount that is together a very sensitive and sophisticated detector of water quality. In fact, the way that a mussel opens and closes its shells is a better detector of water quality than a much more expensive digital sensor. And so here's our first prototype where we're harnessing that living material, that living sensor, by gluing a Hall effect sensor, which is a magnet sensor, to one half of a mussel's shell, a magnet to the other half, and then we're able to harness that ability of a mussel to detect its water quality. And for about $2, we get a better water quality detector than a $10,000 dissolved oxygen sensor. But we didn't do this only to save money, although of course that's helpful because we didn't have a $10,000 budget for this sensor. But we did it because we're very interested in the new potential that we could start combining what we're calling artificial intelligence plus natural intelligence. In other words, we can combine the best the computer has to offer, the kind of holy grail of computation in AI or artificial intelligence. We can combine that with a natural intelligence or a biological intelligence of living systems, an intelligence and a kind of responsiveness that has evolved in many cases over millions of years to be incredibly good at doing things like sensing its environment and responding accordingly. And we think that combination has a really interesting potential to influence how we design and make the built environment of the future. In other words, we're already starting to use versions of digital technology, but that's only pretty recently. But if we can combine that with this kind of biological living system, then we think we can, really create some interesting potentials. And so here you see one of our early prototypes, these lights in the river, and you see a kind of tipping point in the data, so they change colors from a kind of reddish color to a bluish color. That's because the water quality has slightly improved at that point and crossed a trigger point. But I think, maybe more relevantly, you see those lights in the context of the other lights of the city, and that's something we're interested in as well. So not only doing this as a technical experiment, but as a part of the kind of living, breathing life of the city, the skyline of the city, the dynamic lights of the city, the twinkle of lights reflecting off water near the city, and that we could be putting this ecosystem of information and environment into that context. 3, personal communication. So this is a project that we did in a way responding to ourselves, responding to our own kind of trend of being interested in sensors and environmental quality and this digital technology stuff, but also noting that we wanted to be able to explore ecosystems that were not just objective information, but that were a little bit more subjective and related to other things that are important in the life of the city. So this was for a biennale in Hong Kong and Shenzhen, China, and we decided to kind of create a mashup of 2 things that we were fascinated by about these cities that we thought were pretty unique to these cities. One is the culture of street food, eating out in public in these kind of street food stalls. You see some pictures here. And 2 is low-cost electronics, or actually electronics in general, because Shenzhen is a city where low-cost LEDs are manufactured. All the LEDs we've been using in our previous projects came from Shenzhen, but also, as you probably know, this is a region where a lot of cell phone manufacturing takes place. So this kind of combination of street food and electronics was our inspiration to create basically a new kind of soup bowl. I know that sounds a little weird, but here's how it worked. We took these white soup bowls, which are what street food is typically served in Shenzhen and Hong Kong, these cheap white plastic bowls, and we used a CNC milling machine not to create some interesting form, but to scrape away, to mill away a very small layer in the bottom of that bowl in a very precise location, in order to combine it with this, which is a scrolling LED badge manufactured in Shenzhen. And the way it worked was this. We were able to hack into these scrolling LED badges, ask curators of this international biennale to program in messages or kind of text message length provocations, like kind of Twitter length provocations, and then hide that message in the bottom of a soup bowl. So you see here how that works. There's a thin layer kind of carved away at the bottom of that soup bowl, and then you see what our idea. You see what I'm getting at. It's trying to be a magic trick of hiding within a soup bowl that looks normal a scrolling message, and the messages said things like this. These were composed as kind of mini manifestos about the city. By the international curators, and here's another one. And they were written in both English and Mandarin. And then they were distributed through our partners in this project, our collaborators, which were these street food vendors. And here you get a sense of what that was like. So an unsuspecting member of the public would go request their noodle soup from their local street food vendor. they would get served. You get to choose your vegetables and your meat, and you get this broth. And then we would be able to have this kind of magic trick of, on the right you see the bowl when it arrives, and then on the left you see the bowl when you've eaten your food. And maybe more vividly, here's the moment where you might start sensing there's something weird about your soup, but you can't tell exactly what it is because there's still some food in the way. And then over time you kind of discover this message, a totally strange, in some ways funny experience, but really what we thought was it was an interesting way to bring the Biennale out of the kind of gallery and the convention hall into the streets and start an admittedly weird conversation, but some kind of exchange and communication between the international curators and the general public. And maybe more broadly, using kind of humor and surprise as a way to communicate with digital information, but cut through the barrage of digital information we're already always part of in our daily lives. And so you get these kind of strange experiences like this that we think are just a kind of a weird idea, but pointing to a kind of maybe a more profound issue and a more profound future for our cities in the state that they are now. 4, closed-loop systems. So, I'm kind of describing how the evolution of our ideas was working at this kind of phase of the studio. And one thing we started to think about was, with these responsive systems where we kind of work with the inputs like environmental quality and then the outputs like changing the light colors, we were thinking, well, what if we kind of set up an ecosystem where there was more feedback, more interaction, and that feedback was really kind of visible. And that was the kind of premise or the kind of initial thought of this project, which more specifically, for an installation as part of a kind of 30-day exhibit, we started with this physical effect we were fascinated by. Probably looks familiar to you because this is honey on a spoon dripping back into a jar. And you see that it creates this interesting coiling effect because it's a viscous liquid. And then it turns out that if you drop a viscous liquid like honey or like melted recycled plastic onto a kind of conveyor belt, you can create very different patterns by changing the speed of the conveyor belt. So, at first you can create a straight line if the conveyor belt's going pretty fast, or you can create a wavy line if it's going a little slower. And if it's going a certain kind of speed, which is pretty slow and hitting a certain sweet spot, then you can get patterns that are very much like figure eights or even other more complex patterns. So we were interested in a kind of material effect that involved a kind of construction over time, but not super predetermined construction. That was part of our ecosystem. Another part of our ecosystem was moss suspended in water, which we could kind of trigger by shooting it out of a nozzle. So we had 2 materials we wanted to work with. This synthetic material, this plastic that was dropping onto a kind of conveyor belt, and this moss, which we were spraying onto the same conveyor belt. And we were able to change how much of each of them was distributed based on just one variable each. So that was the first part of an ecosystem. And the second part was to control the rate of aggregation of these 2 things by real-time web searches. And what this got us, the premise was a very simple ecosystem. And by ecosystem, I mean like pretend that we're designing a very simple version of Biosphere 2. That kind of ecosystem where it's saying we're creating a mini version of what happens in nature or in the whole planet with a few enough variables that we can kind of monitor them and control them. And in this case, our variables are the synthetic material, the natural material, and what we're calling material of ideas or real-time web searches. And we created this kind of machine in order to explore that, which was basically not exactly a conveyor belt as I described, but instead a rotating disc. Imagine you bend a conveyor belt into a circle. Melting the recycled plastic pellets, dropping them onto the conveyor belt, And the idea of this project was, let's see if we can create an ecosystem and let it play out through some very specific rules, but a non-predetermined form. Let it play out for 30 days without touching it. So we took a lot of care in developing the rules and the range of parameters at the beginning, and then we let it go for 30 days. And here's about the first half of the exhibit. And you see, like many ecosystems, it has a kind of equilibrium at the beginning. It's kind of building up in this extruded form. But for a number of reasons, a kind of tipping point in the data, the material effect, because the moss and the plastic are in some ways in competition for this structure. We get a kind of moment of chaos, a tipping point. But then we keep the system going, because it's playing out the rules. And over time, what we got was a kind of more complex equilibrium of this kind of braiding of about 4-inch diameter tubes. And really, for us, that was a project that was, again, strange, kind of unusual, following a premise and not knowing exactly where it was going to go. But we think it has broader relevance in the context of a rapidly changing world and the possibility that we'll have to get more familiar as designers with uncertainty, with effects and forces that we can't completely control, with outcomes that we can't always predict or know, but nevertheless that we could guide in a certain way through designing rules rather than fixed forms. Now, at that point, we were also starting to think about a variety of things, including using more living materials as part of our design ecosystem. And that was about when we created the proposal for an invited competition, which is for the MoMA PS1 project. And you may know some other projects along these lines. And here was the kind of the idea for the project. So this is the video recreated in the competition phase about something we thought could be interesting to push a new idea of architecture forward for a temporary summer installation in the courtyard of the museum. So this project that we call Hi-Fi basically had the idea that maybe we could explore a new way of designing and manufacturing the built environment with very little waste, very little energy, and very little carbon emissions. And so we started with this, the diagram of the carbon cycle, the kind of Earth's normal, natural, healthy cycle of growth and decay and regrowth. And we imagined that maybe we could create a building by temporarily diverting resources from the carbon cycle and then returning them back to the carbon cycle. In other words, maybe we could take low-value raw materials instead of high-value raw materials. Maybe we could spend almost no energy converting the raw materials into building elements instead of what usually happens, spending a lot of energy to convert the raw materials into building elements. And maybe at the end of the useful life of the building, we could return all of that physical stuff back to the healthy carbon cycle rather than having it sit in a landfill for hundreds or thousands of years. So sounds almost too good to be true or impossible to execute. But the kind of kernel of hope was this, which is mycelium. So this is the root-like structure of mushroom. And you can see it growing in this kind of thin white filament in a microscope video. And it turns out that you can take mycelium and combine it with agricultural waste. So not the high-value part of agriculture, not corn kernels, but the low-value part of agriculture, chopped up corn stalks, the leftovers of agriculture. And you can combine these two together, and as you see here in a sped-up version, over 5 days, it solidifies into a useful solid object. This is a process that had been discovered recently by a really fascinating startup company. They were using it for packaging material to replace styrofoam. And our thought was, and proposal was, maybe we can create architectural elements from this, basically a new kind of brick out of this process. Here's the brick that we designed and kind of engineered with our collaborators at the startup company Ecovative and our structural engineers Arup. Our thinking was, let's test out this new kind of building material and see, possibly if we can make a new kind of architecture out of it. But since no one has quite used this kind of building material to create large-scale outdoor architecture, we had to do a lot of testing. And here is one of our poor bricks being subjected to 100,000 pounds of force in a materials testing lab at Columbia. And you see how it compresses quite a bit, but it actually never fails catastrophically. Our structural engineers were fascinated by that. We also tested an assembly, because you not only have to know what a brick does, but what several bricks, when attached together, will do. And that was not just for research's sake, but it was because we needed to determine, could we make this thing? Would it work? And one of the first things we had to do with our structural engineers was make a structural model. But then everyone very quickly realized that no structural engineering software on Earth has a drop-down menu item for mushroom brick. So if you're going to kind of simulate this accurately, you have to develop a custom material profile. And we did a lot of iterations. And an interesting thing here, I mean, every project probably involves iteration, but here our iterations involved many scales at once. So we were designing the ingredients that went into a brick, designing the shape of a brick, and designing the shape and size of the entire massing of the project all at once. Each one of those was involved in a single iteration. First iteration, we have these red areas, which basically represent major problems, because that's deflection of more than 30 inches in hurricane force wind. So that's not good. But by iteration 7, which was basically all we had time for, we were able to get to an area where we were more comfortable. And this was through this changing of the ingredients of the growing process, the shape and size of the brick, and the shape and size of the overall construction. Another interesting feature of this material, which became kind of a challenge for us, but an interesting opportunity, is that it's different on the inside than the outside. In other words, it has this kind of skin that grows along the outside, but the inside is a little bit more absorptive. And that meant that unlike some typical processes with bricks, construction processes, we couldn't cut bricks on site. Because as soon as you cut it, it's compromised in terms of its durability. So at this point, we used computation to solve two problems that we knew we had. One, was a fitting problem. So every course of bricks was a slightly different length because of the complex 3D geometry of the tower. So we had a fitting problem. How do you create the right assembly of bricks that fits for each course when each course is different? And we also had a stacking problem because every brick has to sit properly on two other bricks below it with at least 2 inches of overlap on each other brick. And that was a problem that we could not solve through some intuitive sketches. We could not solve through some simple rules. And in fact, we could only solve through the use of the computer to iterate through many, many different possibilities, many different rules, and basically determine where each one of 10,000 bricks should be placed and how each course should be aggregated. So we had solved a few problems, but not really every problem of the project. But because the project is a very fast time pace, we had to start construction before we were totally resolved. And we had to solve some problems on the fly. And the interesting thing here was that we brought together two different types of expertise and labor. Graduate students from Columbia who had a lot of experience and expertise with geometry and software, and New York City brick masons who have a lot of experience with stacking things. And together, that combination of expertise was able to solve a lot of problems on site. And that was another interesting example to me of how this process kind of put together different loops of ideas and expertise and thinking. Here, the final constructed tower, about 40 feet, 10,000 bricks, and it's sitting kind of in the context of the glass and steel buildings of Manhattan in the background, and the traditional clay brick buildings of Queens in the foreground. And it kind of gives us this both familiar but kind of completely new type of appearance and type of structure. We were interested not only in the technical performance of this material, but in what we could maybe call the atmospheric performance. So what would it be like to stand inside this thing? What would the kind of texture and color and pattern be for this new material? And that was important for us too, because again, as I've said before, we didn't want to only do a technical experiment with our new idea about architecture, but we wanted to kind of explore it in all of its possible implications. So we wanted to know what it was like creatively to design with this material, not only would it work technically. Of course, as anyone who has kind of seen the pictures of one of these installations before or been to one of these installations before, as any of those people know, the ultimate test of these projects is their ability to host a party. And here you see the thrilling but terrifying moment for us on the first Saturday of operation where 5,000 people come to this courtyard, not to see the architecture, but to hear experimental electronic music. But that was entirely fitting for us because we didn't want to do the kind of project where we were testing only on a lab bench or only in the corner of a kind of vacant lot as a facade prototype. We wanted to do this test kind of in real time, in culture, in society, and kind of gauge that feedback as well as the technical feedback. There was also a moment where we kind of put the project out there and engaged a kind of level of feedback through social media. But really then the experiment continued after the day of construction, just like the original proposal and the original video, because at the end of the project we took down the structure, took all of the bricks and crumbled them into smaller pieces, combined them with food scraps and bacteria, and basically composted the entire building. So instead of construction waste sitting in a landfill for hundreds of years, we were able to return all of the physical matter of this building, admittedly a prototype building, but we returned all of that physical stuff to soil within 60 days and then gave it to local New York City tree planting and community gardens. And again, an admittedly weird project, but the message or the kind of provocation that we think endures here is that maybe as architects and designers and people who kind of deal with the built environment, maybe we should be thinking as much about designing to disappear as we are thinking about designing to appear. So I have just a couple of more projects that I want to show to kind of round out our approach and our thinking in the past year and a half or so. This I'm calling evolution. And so there's an idea that we started to have that, as I've kind of alluded to before, although architects are kind of fascinated by biology and have been for many years, the biology of today is very different than biology of 100 years ago. In other words, you're now able to do things like this, which is grow living cells in a glass chip outside of an organism. You're now able to monitor incredible effects of living natural organisms. This is through the use of a chemical called a quantum dot, an incredible array of microscope images, and you can monitor the neurons firing in a tadpole, a living tadpole, in real time. And you're able to capture images and videos like this, which is stem cells communicating with one another and sending molecular signals and determining whether to grow into skin or muscle or bone. So in that context, with biology representing all these new possibilities, we actually partnered with Airbus, the airplane manufacturer, to explore a kind of new process of design, drawing on these incredible biological systems and also drawing on computation to think about whether this could change the way something really high performance engineering like airplanes could be designed. So with that as the kind of vision, the kind of practical problem we were trying to solve was to redesign the existing airplane piece by piece in a way that would be lighter, more high performance, and therefore consume less fuel and have less carbon emissions. We started with this very simple component that you see in an airplane here called a partition. And this is highlighted in red. It's basically a dividing wall between the seating area and the galley, and it has a fold-down cabin attendant seat attached to it. And it seems like a very simple component, and it certainly is, but to give you a sense of airplane design, this is what a component needs to pass this kind of test called a 16G crash test in order to be certified and fly in planes. And I'm sure we're all glad that this kind of certification is necessary, this kind of robust testing. But it kind of shows you the stakes here. If we're going to try to design a new partition, we're going to need to design it in a way that can match this kind of traditional engineering requirement. So here was basically the problem outline. We have this perimeter shape of a partition. It needs to attach to the fuselage in only 4 points. It needs to have the fold-down cabin attendant seat hanging off of it. And on top of that, it needs to have this area here, the smaller shape, which is called a stretcher flap. That basically means that if someone gets injured in the plane, you need to be able to put them on a stretcher and carry them out of the plane around the corner, around this wall. And because the turning radius is too tight with the wall as it is, you need to be able to remove a part of the wall to make a notch and get this stretcher out of there. So kind of technical aspect of an airplane design, but what it meant for us was we needed to design a structure with a cutout exactly where you would want structure. So it actually is a pretty complex problem to solve. And in this project, we took a natural organism called slime mold, which grows in this kind of adaptive complex network. And the way it does that is it branches in very thin branches and then slowly reinforces the branches that are most important and eliminates the branches that are less important. And it creates networks that are efficient and redundant. They're efficient because they use a small amount of material. They're redundant because they basically connect a series of dots in 2 dimensions in such a way that if you knock out any of the bars or connections, you can still reach each of the dots. You can still have the network connected. So for our project here, we basically created an algorithm in the computer that enacted the logic of the slime mold. It wasn't meant to look like slime mold, but it was meant to use this kind of complex adaptive branching network and basically to be used to create versions of connectivity in 2 dimensions that are efficient and redundant. And we created a version of kind of artificial evolution in the computer that could generate, then evaluate, and then evolve literally tens of thousands of design options. So we have them in the computer. We know how they score in terms of weight and structural performance. We're trying to minimize the weight and minimize the displacement under structural loads. And once they're in the computer, we can do a lot of things that aren't possible through just intuitive engineering design. We can sort them based on design family, shown here by color. We can identify the set of designs that are best performing based on this complex trade-off between weight and structure. We can zoom in and explore the designs, what they look like, how they're working intuitively, and eventually kind of hone in on designs that we are arguing are high performing, but also novel, also unexpected and unusual. And we think that is a process that has a lot of kind of potential for design in other ways, to be able to use the power of computer automation, sometimes informed by kind of biological algorithms, in order to create design solutions that never would have been possible by a human intuition alone. And so how does that work? We have a second level of optimization here, which basically creates each bar shown in the kind of slime mold macro version out of a lattice of tiny microbars. We used a kind of advanced 3D printing in metal. So 3D printing in plastic is becoming more and more common. In metal, it's very challenging for a few different reasons. And we also used a new version of metal itself, a new alloy that was invented by Airbus for this project. So we were designing at the kind of molecular scale of an alloy in new kinds of fabrication with kind of advanced 3D printing in metal and with this kind of biological version of algorithms and evolution and computation. In the end, we created a replacement for the existing partition that was not only 45% lighter, but also a little better performing. And so on the right, you see our design, and admittedly a kind of weird-looking design, but a design that is now being tested in all of the robust ways that components need to be tested to fly. And the track that it's on now is to get certification this year and be flying in A320 airplanes next year. Okay, so that is a kind of technical project, but at this point we returned a little bit to the kind of messiness that we think is relevant and, of course, interesting to architecture. And this was a chance that we used to explore some new ideas about what we're calling social robotics. So this is a design we did for basically a technology event. The Quantified Self community is basically a community of people who do personal data tracking, kind of Fitbits and other things like that. And for this project, they wanted something that would take data, like personal data, and put it in a context that made it interactive and social. So we kind of hacked together a custom spray painting robot that would make drawings in real time that were responding to Twitter data and it would create a drawing, a kind of map of what was going on in the event in real time. And this drawing would not be predetermined, but it would be created based on the content. So these different circles correspond to different topics, but we didn't know how much people would talk about each topic. And we created a kind of drawing that would be a reflection of what people were saying in real time, both in the micro sense, because we're spray painting the actual Twitter messages, but also in the macro sense, because it gives a way to visualize the kind of mood or the kind of gist of an event. Each color represents a different day of the event. And I think just two more things that are on our plate, have been on our plate recently, and one of them is translating some of these ideas and some of our latest thinking to, in some ways, a more traditional building. So this is the design of a small building for Princeton University, actually for their architecture school, and for their research on robot arms and sensors and kind of next generation building construction technologies. And our framework for this building, which is more or less just a simple shed of a building to be most flexible, as flexible as possible, our idea was to try to create a building that could be updated over time. In other words, the researchers there know what they want to do today and next year. They know what kind of equipment they're going to have now and in a few years, but they don't exactly know what they're going to want to do and what kind of equipment they're going to have in 5 years, 10 years, especially 20 years. So we created a kind of platform for a building that could be continually updated and upgraded over time. So we're calling that an open source building. In other words, it's released on day one with a certain set of functionality, like software is released, and then it can be upgraded over time and kind of continually re-released. One example of this is that the building on day one has a radiant heating system, and it's feeding waste heat from the neighboring building into the radiant floor. But there's actually research going on in the Princeton Architecture Department to create some geothermal well experiments, and our system is very much, our building is very much designed to be able to have swappable mechanical systems, swappable heat sources. Also, the facade and roof are designed to be upgraded over time. That's part of the reason that the building is kind of 2/3 enclosed and 1/3 incomplete or open frame, because this open frame will allow the researchers to design and manufacture full-scale prototypes of building or wall sections and roof panels and install them kind of in context. So they won't be studying them kind of out of context, but actually as part of a building. The building will have a gantry crane and some industrial robot arms. It will also be made out of salvaged, out of glue-lam structure, so a kind of engineered wood with a kind of low environmental impact. And then finally, the exterior layer of the building is going to be made out of recycled wood or reused wood, and in this case, out of New York City scaffolding boards. So you see here outlined on the left in white are these big scaffolding boards used a lot in New York City construction. They're typically used for about a year. They're outdoors. They're good quality wood, but they get really beat up. And then after a year, they're thrown away because they get some warping, sometimes cracking. And rather than inspect each one, the construction companies just throw them in a landfill. So we're kind of diverting these boards from the landfill. And rather than trying to kind of smooth over or complain about their imperfections, their warping, their cracking, their knots, we're actually working with the researchers at Princeton to create a system that recognizes those imperfections and kind of enhances them, makes them more visible. So we have a kind of custom robot that will detect features in these scaffolding boards, like knots and cracks, and then treat them in order to kind of call out their most interesting and unique properties, to kind of reveal the variation in wood in general, but especially this kind of used wood. And so here's a sample of some of the effects. We're basically treating these boards with sandblasting, which has the interesting potential to wear away the soft areas of wood, but leave the hard areas of wood. So unlike CNC milling, which would remove everything in the same, to the same degree, here sandblasting has this effect of kind of enhancing the natural variation in the wood and the three-dimensional effects. And finally, the last project, and I'll show this very quickly, but I think it's important for me to note, is a project that we did that was almost entirely a project of atmosphere. And it's important for me to say that as much to myself and my team and my kind of thinking as it is to you. But the reason I'm showing this kind of last and emphasizing it is that just because we're doing prototypes, just because we're engaging engineering and software and material performance, doesn't mean that we're ready to advocate a version of architecture that is entirely quantified and technical. So we think that these tools can be super useful as part of a broader ecosystem, but they don't mean that we should be going in a kind of performance-driven direction for architecture and the built environment. So this is a project we did as a kind of commission for the musician Bjork. She had a retrospective at the Museum of Modern Art last year. And as part of this retrospective, she was basically commissioned by the museum to make a new song and a new music video. This is a kind of trailer from the music video where she was basically created a new work of art that was a song that was very emotional, that had a very important mood, that led to the filming of a music video in a kind of moody context, this kind of landscape of Iceland. And the challenge for us was to create the architecture that would match this song, because the song was going to be on display in the museum. The music video was going to be on display in two screens that were kind of surrounding the audience. And the job for us as the kind of architectural designer was, how do you create the architecture to match that? So in other words, how do you create the architecture for a song, and also how do you create architecture for a mood? We created a lot of different versions of the design and had a lot of feedback and some really interesting discussions. In the end, we did something that was pretty literal, but seemed to create the right balance, which was we took a 2D map of the song, a kind of spectral analysis from basically a music editing software, which creates this 2D map in colors of the song. We projected it onto the ceiling and the walls of the room where the exhibit was going to take place. And then we basically created this field, immersive field of sound-absorbing material, which was felt, to create a three-dimensional texture which would absorb sound, but it would also be a kind of physical instantiation of the song itself. So more specifically, we took a regular triangular grid. We distorted it based on that 2D map, the spectral analysis of the song. And then in addition, we kind of pulled it in the third dimension based on the spectral analysis of the song. So we created a number of cone shapes. Each cone was slightly different, responding to the map of the song. And these cones were then made out of felt in a way that was both kind of computer-driven and handmade. So we were able to take felt, laser cut each cone. There were 7,000 different cones. Each one was slightly different. We laser cut it, so it's kind of computer driven. We only could have known how tall each cone should go based on the computer, but then each cone was actually hand stitched together and placed in its position by a human. And that was not only out of a theory, but that was out of necessity because of our kind of manufacturing technologies available. But this basically created a pretty strange and atmospheric effect where we get a kind of landscape for the walls and the ceiling that was, seemed at once kind of deliberate and based on a kind of intuition and a little bit computer driven, but also organic and kind of atmospheric, and almost like countering the precision of the digital by this human touch. And in some ways, we were very much inspired by the fittingly enigmatic advice of Bjork in one of the design meetings, where she said, well, the thing is, I think modernism in the 20th century was about math and geometry, but this next century will be more organic. And we were trying to channel that. What exactly did that mean? Should that mean the cones were triangles or some other shape? We didn't know. But in the end, we think we achieved this effect where you get this kind of hybrid, which I think much of our work is about, kind of putting different things together to create an effect that is interesting, that maybe suggests a new path, that is more than the sum of its individual parts, and as I was suggesting before, that is not only using technologies, kind of pushing some limits, trying to solve some real world problems, but is atmospheric and creative and part of a more complex and rich future for architecture. Thank you. So do we, have time for questions? Okay, sure. A few minutes. Yeah, that's a great question, and something that I've thought a lot about. We actually have mostly young architects, like recent graduates from architecture school, in our studio, but we do have one computer scientist, and we look for opportunities to collaborate all the time and have a really wide network of collaborators. So kind of depending on how I define the studio, we could either have, this small team that's mostly architects and a computer scientist, but since often our projects are so collaborative, when we work with other people, then in some ways those people are kind of part of our creative process in our studio as well. So recently we've collaborated with a kind of embryologist and stem cell scientist at Rockefeller University, so a kind of serious biology. But we've collaborated with the engineer and kind of provocative artist, Natalie Jeremijenko. We've collaborated with a few different musicians, and in each one, like, we're kind of fully engaging the creative process with that person and with their expertise. Also, we worked very closely with Arup in the project about engineering the bricks, and they felt fully involved creatively as well, and we needed their creativity. And in fact, for that project, it was a great measure of our kind of involvement of them that they were so fascinated by this weird material that was not strong, but not weak in the way typically materials would be weak when they are weak, that they've written several technical papers out of it. And so we're always looking for those opportunities, and that's our kind of way to get outside of our own defaults and cliches. The short answer is yes, but I think the challenges are mainly about durability. So we knew that we needed 3 months, and we basically engineered it to 3 months, but we were pretty quickly able to get the improvements we needed to be confident in it for 3 months. I think there are a lot of ways that it could be enhanced to be more durable, but there's an interesting tension, because we actually could have taken the bricks and coated them with the kind of polyurethane, and then I think they would have lasted for 10 years. But we knew unlike a lot of projects, that we wanted to compost the whole thing afterwards. So again, the short answer is yes. I think this material has a great future for being able to be both robust and potentially biodegradable. I think right now you could replace things like rigid styrofoam insulation with this material, this exact material, and that could work immediately with our existing systems if it didn't have to be outdoors. And it could have this great benefit of not taking as many resources to create and not creating a problem in the landfill. But I think the more interesting thing this led me to start thinking about was if you can have a material that's like really robust but it's not compostable, or one that's really compostable but it's not robust, then maybe you can get somewhere in between. And maybe more than that, just like when, as architects and designers, when we specify materials, we think about their color, their finish, their texture. Maybe we could also start thinking about their longevity. So maybe in some cases we should say this needs to be a 2-week material. If it's for a trade show, why should it be a 100-year material used if it's just for a trade show? But maybe instead of 2 weeks, maybe it could be a 2-month material. Maybe it could be a 2-year material. Maybe it could be a 20-year material, or maybe it could be a 200-year material. But why aren't we kind of specifying that? Why don't we think that that's within our realm to do? Why don't we take responsibility for that? And so I think that's the bigger picture answer to it. I mean, I think the short term is like, sure, these bricks could be engineered to be more robust and more of a replacement for clay bricks. But I think the deeper question is about the longevity of materials. I was thinking of that, Corin, yeah. Well, it's definitely led to a lot of that. And something we had on the table early on was maybe we could actually create a version of architecture where we think about local materials, just like some people talk about local food. So we have a version of describing this where basically everything for the project came from within a radius of 150 miles. Because there is some corn grown in upstate New York. The startup company we worked with was in upstate New York. So we get all the materials from there, manufactured upstate New York, driven down to the city, installed, and then we composted it about 2 miles from the site of the installation and returned it back to New York City, soil. But I think also there's some really interesting potential that this localness could be repeated. And this process, this material will work with corn waste, but also with rice kind of waste. So you could use chopped up corn stalks, but you could use also chopped up rice hulls. And it could be very local. It could eliminate kind of transportation miles. It could be part of a more kind of DIY type of ecosystem of construction. And I've actually heard a lot of ideas by people other than our studio about ways this could be pushed forward in really interesting ways in terms of maybe housing and informal housing situations where people are already building out of waste, out of things they find locally in the environment. Often structures are, 1 story, which would be suitable for this. This material is cheap and inexpensive. You can do it yourself without a factory or, complex machinery. You can make these things. So I think that's one future. And then also, I think just the materiality of the bricks themselves and the material has led a lot of people to tell me about how it reminds them of structures, more ancient types of architecture. I mean, partly that's probably the form, but I think partly the bricks, the organic texture, has led people to tell me about how it's like some traditional architecture in Iran or in Mali. And I think so there's this really, I think, interesting potential for it. And I think it could go different ways. I mean, it could go the more local, participatory, DIY way of integrating with that. But it could also go in the direction of saying, like, look, this could be a part of a industrial farming ecosystem. You know, you could, grow a plant, use part of it for food, use part of it for renewing the soil, use part of it for making bricks. And it could really be industrialized as well. And if we do that kind of process, then it could potentially integrate in some of our other systems. So I think it's a kind of a provocative type of material in a few different ways.
It seems.
Well, I love the way you say that, and that we had a little bit of that in mind while we were doing it. I mean, we were very interested in this kind of hybrid approach and this kind of a combination of the digital but the biological, a combination of like new technologies, but also you could say the ancient technology of mushroom roots, the ancient technology of the forest that has like, been developed without us, over many years. And then I think we were trying to play with that line in our thinking of the form, in the texture of the bricks, and deciding in the end not to treat them very much or color them. So I think is the question, what are some biological materials that could be used for structural applications in the future? I think it's tough. So I'm not going to give you probably a very satisfying answer to this, but we had been trying to work with biological materials for a while, and had done some collaborations with biologists about using bacteria to create new kinds of biofilms. And I think there's some really interesting potential there. And some of those bacteria can be kind of modified to create materials that are more or less like we want. And that's a really odd and I think promising hybrid between like engineering and natural systems. For this PS1 project, we chose to use mycelium because we thought it was like ready for prime time. I mean, we were able to manufacture at scale. We knew that there was a chance we could make 10,000 bricks. I mean, we didn't know we wanted bricks in the beginning, but we knew that this is something that was viable now. And even so, even with the most viable now type of biological material, there were moments where I just thought maybe this is not going to work, So we really had to push it to get to that limit. But I think there's a couple of possibilities for the future. I mean, one is that there could become this kind of tipping point or avalanche of new possibilities as typical plastics are replaced with kind of bioplastics made by bacteria that are tuned to create the kind of polymers that normally have to use petroleum, but now you can just use sugar as a resource. So I think that might be coming, and I think that's being driven by research in biofuels and medicines from biotechnology. But it's, as I've learned from my collaborators, it's going to be pretty easy to transfer that technology to building materials. So that's one possibility. But also you could say, I mean, technically I could answer your question by saying engineered wood. Wood is a biological material in a way. And I think we're already seeing some really interesting possibilities with glulam structures and cross-laminated timber. And although, I think it needs to kind of be debated, what are the pros and cons of those systems? I mean, but I think it offers some interesting possibilities if we could make, long spans and, kind of high-performance structural members out of wood, which is renewable. And I know there's other ingredients in this engineered wood, but I think that's offering some new possibilities. So I think it's not a surprise that you're seeing, like every couple of months, some new wood skyscraper or, you know, new wood high performance building, because people are really ready for that. People are thirsty for that. That seems really promising. And I think, you know, it's a buzz technology in the best sense of that. Like, we need a lot of research in that. It's like no single firm is going to master what it's like to build a wood structure building more than 4 stories. But if 10 firms are each doing it in their own way and even debating about the better way to do it, I think that can only be good for the kind of industry and that potential future. Great. Thank you.